Okay, I believe we're back. I'm just going to pull up a paint window here so I can get some drawings going, and then just make sure I can see what I'm doing here. Okay, so I guess I'll begin with my first topic of evaporative cooling. So that's not too complex of a topic, but it is something that not a lot of people think about. So I wanted to bring this up to you guys because I think it's a cool idea, and it's something you can try on your own, because it may be relatively useful if in certain circumstances. So what I mean by evaporative cooling is basically what the name states. It's just that you can cool something by evaporating water. And so I will explain a little bit of the science behind this, but I'm just going to explain the scenario first. So there are a couple different names for evaporative cooling. Some people call it a swamp cooler, some people call it a desert cooler. This is basically just, it's something that is not very sophisticated in terms of the mechanics behind it, but in terms of the science, it is fairly practical and relatively efficient in terms of energy needed. So if you want to get as simplistic as you possibly could with evaporative cooling, then we can think of this scenario. So let's just imagine that you have a water bottle, and so there's a water bottle and it's got the cap, and so there's water in it. Obviously it's a water bottle. Now the situation I always think about, because growing up I always played soccer, so I would bring water to the game, and if you just have a small water bottle and not like an actual thermos or something, then the problem is you'd go in to play, and then when you come back out of the game, your water has been sitting there in the sun and it gets extremely hot. So the sun's just beating down on it and the water temperature goes up. And so hot water isn't the most refreshing thing once you just came back from running your butt off in a soccer game. So one way to get around this is if you have a towel or a little rag or something, you can take this rag and pour a little bit of the water on there so it gets a little wet. And so then you just wrap the rag around the water bottle, and so the rag is just encompassing the bottle. It doesn't necessarily have to be in any specific manner. It's just that you want it to be in contact with the plastic on the bottle. And what happens is the water that's on the rag evaporates, so I guess we'll just use blue. It comes off, and in the heat of the day, the sun, obviously, I live in Florida, so it's a problem that happens a lot. Well, it's not necessarily a problem, but it's something that I have a lot of experience with. The sun beating down and evaporating water. So the water evaporates off of the towel, and what happens is when water evaporates, because it has such a high specific heat, it will suck the energy out of the surrounding area in order to get it to bump up to the level where it can become steam or water vapor. It's not necessarily steam because it's not 100 degrees Celsius, but the idea is that the water can take energy from around it and use that energy to get to a higher level and change state. So to explain some of the science, and just to get my point across, when that happens, it takes the heat from the water that's in the bottle, and then so then the water in the bottle actually becomes cooler because the water on the rag is evaporating. So if you have, and this is something I've been exploring in my thermodynamics class, so if you have the enthalpy, which is H, and the temperature here, and we make a graph, then you can make this bell curve shaped graph, which is like, oh, that's terrible. So you make this graph, and it looks kind of like that. That's kind of butchering it, but so what happens is you have your temperature and you have your energy. And so let's say this is a fluid to gas graph, because we're talking about water becoming water vapor. So what happens is, let's say you start with fluid water, so HF, and it's right here. So that's where you're at. You're right here. And then you put it out in the sun, so it's on this rag, and you put it out in the sun, and the sun raises the temperature, so the temperature goes up. So then it goes up this little line here, and it gets to this temperature. So the energy has increased as the temperature's gone up. So now it's at this temperature, which is a new energy level, which we'll say is HF2. It'll be a little hard to draw, so that's HF1 and that's HF2. So then now you have a hotter temperature for your liquid water, but what happens is if you want water to become steam or water vapor, then you can't just keep increasing it. Like, the temperature doesn't just constantly increase. What happens is when it reaches the point where it can become a vapor, then you have to cross this gap of energy to reach the other state, which this side is gas. So this is liquid, and this is gas over here. And you may say, well, there isn't a specific border between those, and that's true. So what happens up in this area up here is it gets a little confusing about whether it's a liquid or a gas, and what happens is it isn't necessarily either of them. It kind of acts like both, but that's for another day. So what happens is the energy increases, and then it has to jump across this gap, so it needs a buttload more energy just to change state. And what happens is, if you actually look at a graph of the temperature of liquid as you're heating it up, once it starts boiling, it doesn't necessarily get any hotter, because what's happening is all of that energy that you're putting into it in terms of heat is actually being absorbed by the molecules, and it's being transferred into the process of converting the water into a water vapor, as opposed to just going straight into raising the temperature. So if you look at a graph of the temperature, it will actually, versus time, it'll actually go up, and then it will plateau a little bit, and then it'll go up again. Because at this point here, everything's gas. But at this point here, everything is water. And over this period of time, the substance you're working with is changing state. So it's this gap right here which is actually what we call the specific heat. So based off of the temperature it's currently at, you need more or less energy to jump to a higher, to the next state, which is why if you have water sitting out while it's fairly close to freezing, then odds are it won't jump the gap because it can't find the extra energy to turn into steam. But if you have water that's fairly close to 100 degrees Celsius, then even though it isn't 100 degrees Celsius, some of the water will still jump the gap and become steam. And this is why we have a property called water. We have a vapor pressure when you have a liquid, because what happens is you have a graph of so you have most of the molecules are built up here. So this is the number of molecules or percentage of molecules or whatever, and this is temperature. And we'll say that this is where the temperature is for a phase change of that substance. Well, most of the molecules are at that temperature, and that's why you get a average temperature that is lower than the boiling point of that substance. But if you look at this graph, and this is kind of a poorly drawn graph, but it at least shows the idea. There are some molecules that are moving fast enough and flailing around fast enough to where they can become, they can make that jump because they have enough energy, internal energy, to become a gas. So then that's why we have a little bit of a vapor pressure when you have a closed container, because some of the liquid does evaporate, even though it's not at the temperature, it's not at an average temperature where it would evaporate. But so what happens, like I was saying, is that the process of evaporating water is I believe it's endothermic. Yeah, endothermic. So it requires energy. It does not. It doesn't shoot out energy as it occurs. It's an endothermic reaction. So it means that you need to jump this gap in order to cause the reaction. And I know it's not necessarily a chemical reaction because it's a phase change, but it is a good analogy in terms. So what happens is when you have the water that reaches this point and evaporates, it will draw in the energy from the surrounding area, and the largest pool of energy would be this bottle of water that it's stuck to. So then when you come back from playing soccer, then the water that is in the bottle is now cooler, and you may think that it wouldn't be too much of a temperature change, but you would definitely be surprised. I implore you to try. Just get like a towel or even some like napkins and wrap them around your water bottle, and then while you're about to go do something, and when you come back, the towel will be drier and the water bottle will be colder. No matter what temperature water you put on the towel. So that is the idea of evaporative cooling. So I've pretty much explained everything I wanted to in that topic, and I'm not seeing any questions, so I will play an ad and transition into my second topic, which is relativity.